Hello, everyone. Yeah, my name is Zhiping Yao. I'm a principal engineer and a senior director of Alibaba Cloud. So today, my topic is from vision to execution, the story of Alibaba's home-built 51.2 T switches. In last 10 to 20 years, for general computing, the data center network actually is the cloud architecture dominate the data center networking. Which we believe there are four essential elements in data center networking. First one is cloud architecture. You have a very good scalability and the resilience of a multi-path, right? So many links, any link or any switch failure, you're gonna ECMP or swap to the other link. This is provide very resilient network, so it become very popular in the last 10 to 20 years. Actually, all the hyperscale, they use these topologies. The second part we believe is the white box movement in the last 10 years contributed greatly to this big improvement expansion of the cloud architecture data center networkings. The third part is open source networking, right? The laws such as Sonic, which the previous speaker just mentioned, is very popular right now. The fourth part we believe is that the swappable pluggable optics also contribute to these great expansions. In the last 10 years also, right, we experienced actually 4 generations of the network expansions, like 40 gig, I believe it's in 2014 time, 40 gig networking and 100 gig networking in 2015, 2016, and 200 gig and then 400 gig right now, and in the future, maybe 800 gig and even 1.6T networking, around the corner. Everybody know in last year also we experienced our AI tsunami, right? So it's triggered by ChatGPT last October. And high performance RDMA network become extremely important in our AI infrastructures. So here is our answer to this, the high performance networking. We call it HP7 Zer. We believe, we found out that cloud architecture is still the best fit for high performance networking, but with some improvement. The first part is we think the large radix scale is extremely important in AI, machine learning networks. The second part is, in the GPU network, we have a new switch domain we call in NVIDIA is called the unveils switch. That domain actually provide multi-rail communications for all this training work, right? So we have to incorporate these new features. The third part is for the low entropy issues, for the load balancing issues in this very high performance network, adaptive routing could be a solution, right? So we believe we have to make this working, right? So the last part we believe because the high performance networking become very sensitive to packet loss and any link failures, we believe seamless integration between our loss, our Sonic, and in-house automation tools are extremely important. So the HP7 Zer architecture is our answer to the AI emergencies. The key part actually here is we try to put as many GPU as possible under a single TOR switch. Actually, it's not TOR. Today, top of rack, actually top of multiple rack, it could be dozens of rack and hundreds or even thousands of GPUs under one tier network. The topology here is a 3-tier, right? The first tier used to be called TOR, but today it's top of multiple rack. For this network, we can put roughly 1,000 GPUs under this layer. We call it segment. The second tier is we call it like a spine leaf or leaf switch, right? So the leaf switch it's like a pod. Pod can have dozens of different segments. Then the whole pod, the 2-tier network, will support up to more than 10,000 GPU servers, 40 gig, 400 gig. And so that one can make the network working really, really easier than 3-tier network. Of course, we can extend to 3-tier network, which can support up to hundreds of thousands servers. Yeah, this is our vision of the high performance network. Okay. In this diagram, every switch here is, we have to make the scale out. The switch need to be as high bandwidth as possible. Here, Tektron is our cornerstone of our high performance networking. Tektron is Alibaba's 51.T fabric switch. It's a 51.2T switch ASIC Tomahawk 5 today. We choose the configuration of 128 by 400 gig QSFP112 form factors. It's a wireless VSI design, and the network OS is solid inside. We pour on this box and pass track since December last year, and we're making the production, in July this year. We choose the QSFP112, the 400 gig optics, right? So it's a QSFP112 MSA compliant. It supports different type of optics. It's like a VR4, SR4, DR4, FR4. And of course, the fun part is we also support linear pluggable optics. This is the cornerstone of our high performance network. This is the system architecture of the Tektron switch. And on the bottom part is a hardware platform. The key part actually is a 51.2 switch ASIC. Of course, you have a CPU, the control module, and the BMC, the management, the BMC modules. Right? Above that is our software platform. Our software platform is built upon the SOLIC. And of course, we incorporate a lot of our own stuff, such as our development, DevOps, Warden Dockers, and our telemetry Dockers, etc. So a lot of us, our own system built upon that. So this is the whole system architectures. Hardware platform actually quite simplified. Actually, we follow the philosophy of we have to separate the data plan, control plan, and the management plan. Each plan we make it standardized and modularized. For control plan, CPU plan, we have open control CPU modules called OCM. We standardize all the pinout and the form factors. For the BMC, we also standardize the BMC modules. The most important part here is for the data plan, the switch modules, we also try to make it standardized. We call it the removable switch modules. The removable modules can be easily removed or swapped from the chassis, enable very composable design, right? You can imagine you can change to different ASICs, right? You can. Hello? Yeah, so it can change to different ODM vendors, right? So this is the hardware platform. We try to make it more modularized. For this system called it Universal Network Platform, you can see you can easily remove and swap the data part, right? The switch modules, ISM. Here is the system top view from. You can basically have a three part. The front part is like a 128 QSFP12 connectors and 51.2T switch ASIC, the joint heatsink there. In the middle part is all the control paths and the management entity, right? And such as OCM and the BMC, SSD, and the real side of the chassis, of course, is the factory or power stuff, right? OCM is open control module. Today we use ASLEC D CPU. It could be changed to other CPUs or AMD CPUs or ARM. It supports dual channel DDR modules. It supports up to, today we choose 32 gigabyte, but we can upgrade to 64 gigabyte. It's a PCI Gen 4. And it's a standard open control module. We define all the pinout and form factors. We believe it fit the future, the networking control plan usage. We also standardize the BMC modules. We reuse the SODIMM 260 pin connectors and define all the signals. So it can be easily swapped and upgrade to the future. Today we use the ST2420, the BMC chip. ISM, the fun part. ISM is we call it removable switch modules. It can be swapped from the chassis. so you can change the form factors. Today, we use the QSFP 112. Could be changed to like OSAP. It could change to the co-packaged optics. So I could change like different. You can support different chips, right? Today's Tomahawk 5 could be NVIDIA SP4, could be Cisco G200, could be Marvell TL10, and it support air cooling or liquid cooling. The most interesting part is we can, work with the ODMs. I can have multiple ODMs to work on the same project and can be swappable. Here's our major ISM 128Q is 128 by 400 gig QSFP 112. You can see you have a switch for an LAN card. We put as many QSFP in the faceplate as possible, right? So for each PCB, for the switch modules can come out like 88 QSFP connectors, and the LAN card is 40 of them. ISM family, we're working on multiple ISM right now. Today is 128 by 400 gig. The QSFP 112 is already productions. It could be changed to 64 by 800 in the future, probably our next generation networks. And the fun part is here, cold plate liquid coolings. We're working on the cold plate liquid coolings. Of course, there's many more ISM on the way. Fun part, cold plate liquid coolings. In last couple of days, I believe you guys probably see a lot of talk, a lot of demos about liquid cooling, right? It could be the answer for the future AI infrastructures. We believe the cold plate liquid cooling gonna be very popular in the next 2 to 3 years. So we're working on the liquid cooling switch. So here is the top view of the liquid cooling switch. The most I try to emphasize it's not only liquid cool the switch ASIC, which is about 800 watts today, right? We also doing the cold plate for the 128 QSFP connectors. You can see it's a very challenging design for the QSFP, how to cool the modules, right? That's a very challenging design. But we successfully make it work. About 2 months ago, this system already working right in our system. It's really happy to see that. Fun part, linear pluggable optics. I think about a half a year ago, Andy from Arista, right, drop a bomb in OFC, say, hey, the linear pluggable optics is very promising, which I believe so, right? So the Tomahawk 5 112 gig Paragon DSP SerDes is quite capable to interface with the optical engine, right? So our switch actually is designed to meet the VSR standard, right? But the industry, the ORF tried to define the 112 gig linear pluggable standard, which have a much strict the requirement than the VSR standard. So we start to test linear optics roughly maybe about half a year ago. We found out that our system it's very capable to support linear optics. We test both SR4 and the DR4, right? So the DR4 actually has a better BER than SR4, I believe, especially silicon photonic DR4, which have a great linearity. And SR4 is not bad. We test like maybe close to 10 different vendors, and the SR4 BERs, all of them are more than, the BER is better than E-6. Some of them are maybe E-9, and under different temperature environment, right? So it's quite promising. It's quite promising. But there are challenges of the LPO. I think the first thing is that first challenge is how to standardize the LPO's test point and how to deliver and manufacture this, so how to test this, how to qualify this is quite challenging. The second part, I think the sensitivity of the LPO, the lower sensitivity of the LPO should make some improvement inside the optical modules, right? The TRA, CTLE, and maybe even how to optimize TX power and the laser power inside the LPO. The third thing that we believe is that interop with different DSPs. So you have to interop with different DSPs. DSP optics require additional test for both LPO and DSP. It's very challenging work, right? System level production need to very close coupled with the switch, right? With the Tomahawk 5 switch. The last part is that how to deploy it is extremely important. We believe the end customer like us can use this LPO. It has to be deployed in well-controlled environment, well-controlled end-to-end, define a scenario. For example, the initial deployment, we believe it's maybe Tomahawk 5 to Tomahawk 5, right? Tomahawk 5 to other switch chip need more testing. So it's quite challenging, it's difficult to use, but it's very promising. For this Tactron switch, we already mass production since July this year. And our first deployment is with the traditional DSP optics. And we plan to pilot test the LPO at later stage, probably end of this year or early next year. And the UMP system is thriving, like I said. The UMP, because the ISM and the switch module can be swappable, it's easy to enable multi-source, right? So it's great for us. A quick summary. We believe that class network architectures dominate data center network in the last 20 years, so it will continue to do so in the next 5 to 10 years. Of course, with some improvement or some new features need to support it. Network disaggregations, white box switches, pluggable optics, and open source network OS such as Sonic, all of them play a very vital role in the great expansion of the data center networks. The ongoing advancement of the semiconductor technologies are driving the innovation in switch ASICs. It's like today, 51.2T ASIC is the leading edge switch, right, this year, but 100 gig switch or even 200 gig switch ASIC are coming soon. It will increase the speed and bandwidth dramatically in the next couple of years, I believe. The last part is the data center switch system need to consider silicon and optic co-design methodology, especially for linear pluggable optics, right? It's like the series, the driver part is on the switch ASIC, but the optic part is on the optical module. So you need a whole system design. You have to co-design. Call to actions, we believe openness, right? We believe openness lead to greatness. So it's like we have a lot of contributions to Sonic. It's like UMP and OCP networking project, right? So UMP today is not a public, but we released the spec to 5 of our partners, and they work with us, on the new projects. We also some other industry, the QSAP 112 MSA, which we believe is good for our HPN network. Right? This have a lot of information there. And so, of course, we have OCM spec, the open control module spec. We contribute to the China the ODCC standard. Right? So welcome, to join us. Yeah, I think that's all from me. Thank you very much.